Opportunity to talk to you. This is a meeting in which one of the prime focuses is the Anderson model, and I have a little bit to say about the non-self-adjoint Anderson model, which dates back to about the mid-1990s. Ilya Goldscheid will be saying a lot more about that problem this afternoon, but I also want to tell you something more generally about the theory of spectral theory of non-self-adjoint linear operators, which is full of problems which one doesn't encounter in the self-adjoint theory. I suppose I should apologize in some sense for the fact that many of the kinds of theorems which you would like to be extendable from the self-adjoint to the non-self-adjoint context cannot be. In this sense, I'm a bringer of bad news, but I hope you won't end up wanting to kill the messenger. It's not my fault. There are two attitudes you can take towards the kind of phenomena which you discover when you start dealing with non-self-adjoint operators. One, these are horrible pathologies, and thank goodness within a few days you will have forgotten everything I've said to you. You can get back to your self-adjoint world where there is so much more that you can do productively. The other is that this is the beginning of a fascinating new subject. Well, I've been in it for 10 years, so I think it's fascinating. And you just have to get used to the fact that what happens in this subject is not what you are familiar with in the self-adjoint context, and you have to build up a new kind of intuition. Well, you will see that what I have to tell you is not terribly deep, but let me get on with saying something about it. I'm going to start off by describing the kind of problem which I'm going to be looking at, which you will see is not just Anderson models, but also non-self-adjoint discrete Schrödinger operators. Then I will go on to discuss periodic potentials and what I'm calling dislocated periodic potentials, and then go on to pseudo-random potentials, which is much closer, in fact, in some ways, much closer to the non-self-adjoint Anderson model, and then finally discuss methods of getting some sort of bounds on the location of the spectrum of the operators concerned. So that's my goal, but in the end the goal is more to try to familiarize yourself with the fact that your self-adjoint intuition is not a good guide to what happens in this many aspects of this subject. So the particular operators that occur in the non-self-adjoint Anderson model, as far as I know, were first discussed by Hatano and Nelson, but Ilya Goldscheid will no doubt try to give you a more accurate historical account of this. This is where I first learned about it, anyway. Yes, good. And then there was a series of papers by Goldscheid and Korozenko, who I have said all the theorems, that is, actually, Hatano Nelson's work was numerical observation of certain fascinating numerical behavior. Goldscheid and Korozenko actually gave proofs that what had been observed numerically was in fact true, and gave you a lot more information about what was true than Hatano and Nelson had actually appreciated. But what I'm going to be talking about differs in a subtle but actually crucial way from the work of Goldscheid and Korozenko, which is in fact much harder. Okay, so let's start at the beginning with a large, I mean, this doesn't look particularly large, but a large n by n matrix. I'm going only to consider one rather special case, but it's fairly typical, in which the diagonal entries are random real values, Vn. In fact, there are 7. This is a 7 by 7 matrix, whereas the off-diagonal matrices are two distinct real numbers. Now, right at the beginning, one has to make a choice of the boundary conditions. So at the bottom left and top right corners, I've put A or B as question marks. How should one choose the boundary conditions, and how does this affect the spectrum of the operator? So the first thing is the Dirichlet boundary, the periodic boundary condition case in which you do enter the A and the B in those two corners, and I'm going to start off by putting the potential V identically 0, in which case this is a normal operator. You could take the discrete Fourier transform and you discover that as the size of the matrix gets bigger and bigger, the spectrum converges to the boundary of this ellipse. So in the case where A equals B, where it's self-adjoint, this ellipse degenerates to the interval from minus A plus B to plus A plus B. On the other hand, if you take Dirichlet boundary conditions, DBC actually, then the operator is similar to a self-adjoint operator, and the spectrum is entirely real. So here is the first rather unpleasant phenomenon, that the difference between the two cases consists of just a rank 2 perturbation in which you either do or don't put A and B in the two corners, but the asymptotic spectrum is completely different. It's not that one is contained in the other. One is an ellipse and the other is an interval. One is real and the other is non-real. And as the size of the matrix gets bigger and bigger, the perturbation is in some sense constant. I mean, it's a rank 2 perturbation in all cases. So you are familiar in the self-adjoint theory of Schrödinger operators that when you have a self-adjoint perturbation of rank 2, it can only change the spectrum very slightly. Here, you make a rank 2 perturbation, it changes the spectrum completely. And that's one of the initial things one discovers in this subject. Okay, so now I'm not going to be dealing with this problem. This is the kind of problem, though I expect you'll be dealing with much more general cases, that Ilya Goldscheid will be talking about later this afternoon, at least I expect so. I'm going to be dealing not with the finite periodic problem as the size of the lattice gets bigger and bigger. I'm going to be dealing directly with the infinite volume problem. So we should think of this not as being a finite matrix, but as acting on little L2 of Z, and it's got an infinite number of entries on the diagonal, all of which could be, for example, independent random variables. And then there are two constants, which A and B, which occur on the infinite number of entries just above the diagonal and the infinite number just below the diagonal. And of course, in this case, since it's infinite in both directions, the A and the B, which give you the boundary conditions, don't arise. Now, the next shock is that the spectrum of this kind of operator is nothing like the limit of the spectrum of the finite matrices with periodic boundary conditions as the matrix gets bigger and bigger. There is a connection, namely, if you take the finite matrix with periodic boundary conditions and look at its spectrum and look at what happens as it gets bigger and bigger, then the limit set is contained in the spectrum of the infinite volume operator. And the reason why these two are different is something which can't occur in the self-adjoint theory. So let me, I should have done this before the lecture on my transparencies, but I didn't. In the case where you have a finite matrix with periodic boundary conditions, and then you make the matrix get bigger and bigger, you discover that the spectrum is typically looks or converges to an object of this kind. I mean, this is just an example, but two real intervals and a closed loop like that. The interior of that closed loop is not in the spectrum. So you get some curves, and the eigenvalues approach those curves and get denser and denser on them. However, if you take instead the infinite volume operator directly, then you can have a point out here which is still in the spectrum of the infinite volume operator, but nowhere near the spectrum that you get by taking a limit from the finite volume operators. And the reason for this is that if you look at the resolvent norm at a point like that, although that is not in the spectrum, it has got a resolvent operator for each finite volume. And you look at the resolvent norms, and they diverge rapidly as the size of the interval gets bigger. And so these resultant norms go to infinity as you make the interval longer, and in that sense you would therefore predict that the resultant norm is infinite for the infinite volume operator, which means, of course, there isn't a resultant operator, and that point is in the spectrum. So you have this phenomenon which can't occur in the self-adjoint context, because in the self-adjoint context, the size of the resultant norm is always equal to 1 over the distance from the point to the spectrum. And so if something isn't in the spectrum of the periodic operator, then the resultant norm can't possibly blow up. In the infinite volume case, not only can it do so, but it actually does. So you have to decide which you think is the right operator to study. And this is not entirely obvious, because if you look at a situation where you have a large finite lattice with a resultant norm which is 10 to the minus 20, so 10 to the plus 20, then that means that although that lambda is not an eigenvalue, there must exist something which is so close to being an eigenvector that is actually indistinguishable from one. That is a vector such that when you write down the eigenvalue identity h phi minus lambda phi, the error is of order 10 to the minus 20, which means it's not visible in any numerical calculation. So should such a thing be physically relevant? Well, you can regard it as, in some sense, as being a resonance. It would, if you looked at the evolution of this quasi-eigenvector over a long period of time, it would behave in exactly the same way as an eigenvector until an enormous amount of time had passed. Now, I don't want to try to tell people who know so much more about the way physicists think than I do whether you should think one about the limit of the finite volume problem or about the infinite volume problem. My job is just to tell you that these two things are entirely different, and so you have to decide which one to study. And Ilya Goldscheid has got the limit of the finite, and Boris Korosenko, who's probably also here, maybe he's not. He's heard my talk several times. So you have the two problems, and I want to try to explain the problem where you look at the infinite volume operator directly and try to understand something about its spectrum. Okay, so here is another problem of a similar type, but I'm now going to periodic operators rather than random operators. And this is a very recent paper of Gostesi and Kochenko on a one-dimensional Schrödinger operator with a complex periodic potential. And you can take this potential to be C infinity, if you like. Now, when you want to analyze the spectrum of such an operator, you immediately think that you can use the block wave decomposition, and indeed you can. So you then go through the normal process and you get a complete analysis of the spectrum. The spectrum, instead of being intervals in the real line, as in the self-adjoint case, with possibly gaps, turn out now to be closed curves, which may or may not cross each other. And the problem is the following. If you think that this is simple, then you might think that the operator you get is simple, and that you can do a detailed spectral analysis. In other words, you might think that you can get a spectral projection for every subset of the curves which the spectrum lies on. And now there is a formulation of that, which is that there is a countably additive projection valued measure associated with every Borel subset of the spectrum. And although the spectral projections will not be self-adjoint or orthogonal projections, there will be nevertheless the kind of countable additivity which one is familiar with in the self-adjoint context. The spectral projections will have norm greater than 1, but maybe that's just a price that you should be prepared to pay. Unfortunately, this hope is not realized in all cases. The problem is that when you do the block wave decomposition, you find that everything is more or less as you would like, except at points where these curves cross each other. And where the curves cross each other, you can get Jordan matrices turning up, non-trivial Jordan matrices turn up. And if you look at the spectral projections which contain, for an interval on the curve which contains such a point, you discover that the spectral projection has infinite norm. In other words, it's not well defined as an operator. So although these operators do all make sense and one can do the block wave decomposition, the idea that there is a good notion of spectral projection for every interval in one of the relevant curves is not always satisfied. And what this paper actually studies is when this is actually possible. Being similar to a normal operator is also another way of putting it, is saying that it's a scalar type spectral operator. Another way of putting that is saying that you can define spectral projections as bounded operators for every Borel subset of the spectrum. This is not always possible, and so the starting point of much of the more detailed spectral analysis of such operators gets into enormous difficulties if you have parts of the spectrum which cross each other. And of course, if you have a periodic operator, you can see exactly what's happening. You can see exactly why there are problems. You can do this yourself in a discrete case where the potential has period 2, and even there the phenomenon occurs. So there are difficulties in going on to more detailed spectral analysis of such operators. Now, in the two-dimensional case, or the one-dimensional case, you can do this analysis, and you can work out a lot about the spectral properties from the block wave decomposition. But what I'm going to talk about here is some work of James Hinchcliffe on the case where you have a dislocation. Now, this is a finite matrix, and you see that you have above the diagonal A's and below the diagonal B's, and on the diagonal it alternates between C and minus C. But if you go from around the center of this matrix, you see that instead of having a C and a minus C, you have two C's next to each other. So you have an alternating periodic potential, but there's a dislocation at the origin. You could actually have noticed that there is actually another dislocation because going between minus C at the bottom right-hand corner and minus C at the top left-hand corner. And I must say I've forgotten to put in the two things here, which is an A and a B at the other point. So really for this operator there are two dislocations, but if instead of being an even size matrix, it was an odd size matrix, if I'd put another entries down here, A, C and B, then there'd only be one dislocation, and that would be at the origin. So one can look at these problems both in the finite and the infinite volume, and here is the results that Hinchcliffe got here in this case. Now, there are some parameters here, and this isn't the spectrum of one such operator. This is an overlay of the spectra of various operators of this type. So let's go back to it. We're going to keep the constants A and B fixed during this discussion, and we're going to let the constant C, which is the potential which has this dislocation at the origin, gradually increase. Now, if C equals 0, then you're going to get an ellipse, which, if you look at the inside curve, is not far away from being an ellipse. So this one goes up a bit here, and then comes across here, and then down a bit, like that. So that is the curve you get for a small positive value of C. As you increase C, that is, as you increase the importance of the alternating sign potential, then the curve moves in this way and up that way. And then there is a certain critical value of the constant at which a single isolated eigenvalue appears here, and as C increases, moves across that way, and the same thing happens down here. Now, of course, it has to be both places because this is a real operator, And so if anything is an eigenvalue, the complex conjugate is also an eigenvalue. There is no particular reason why the eigenvalue should emerge from a point like that. If you're familiar with the self-adjoint theory, of course you know that in typical situations with self-adjoint operators where the potential goes to 0 at infinity, the eigenvalues always emerge from the origin and go downwards. And I used to think once that they emerged from the origin because this was a threshold for the symbol of the free operator. And in fact, with self-adjoint multibody Schrödinger operators, you can have the same phenomenon, but in all cases, the eigenvalues emerge from one of the thresholds of the multibody terms. In this situation, there is no threshold at all here. The symbol is a smooth symbol. It has non-zero derivative everywhere, but there are eigenvalues which emerge out this way and out this way. Now, the reason they go to the right is in fact not impossible to understand. What you've got here is a symbol which is alternating between plus and minus. I should have looked at the case of an odd size matrix, and in fact in this example the matrix is 401 times 401, so there is only one dislocation, and that dislocation consists of having two positive values next to each other. So in some sense you've got a bit more repulsion at the origin than you would typically have if it just alternated in sign all the way along. And so you would expect that if there's an isolated eigenvalue, it would be moving off in a rightwards direction rather than in any other. What's a bit surprising is that it actually moves exactly horizontally when it emerges from this point at the critical value of the potential. Anyway, that's the sort of phenomenon you get. For large enough C, the potential is dominant, and the spectrum is really more or less just plus or minus C. For very small values of the constant C, the potential doesn't really matter, and the spectrum converges back to the ellipse. But there is this extra point, and as C gets bigger, it moves further and further off to plus infinity, which is a surprising direction for it to go, but that's what it does. Yes, that would be like, so C equals 1, 2, 3, 4, 5, so on. Yeah. Okay. Now, if you go on to looking at the two-dimensional operator, then you have a free operator which has got 4 terms like this. So this is a right shift with a constant A1, a left shift with a constant B1, an up shift with a constant A2, and a downshift with a constant B2. So that's a sort of generic nearest neighbor non-self-adjoint translation invariant term. And then you add on a potential, which I'm going to start off by looking at being periodic of period 2 in each direction. And here you see the spectrum consists of this shape. There's a hole in the middle, which may not be immediately apparent. Of course, this is a periodic operator, so you can do a full block wave analysis. There are 2 angles here, the theta angle horizontally and the phi angle vertically, so in some sense the spectrum is the image of a torus under a certain nonlinear mapping from the torus into the complex plane, and you can certainly imagine that that is the case. So that's what happens when you do the analysis of the periodic operator, but now you can do a similar analysis for the periodic operator with a dislocation along here. So this is alternating and this is alternating, but notice the plus against the plus here and the minus against the minus. So just as in the self-adjoint case, you should expect to have some bulk spectrum associated with what's happening deep in this region, which is of course exactly the same as what's happening deeply in that region. And then you should also expect to have surface waves which travel up and down that boundary, which are localized in the horizontal direction but not localized in the vertical direction. And you get exactly that kind of phenomenon. Namely, you have this kind of spectrum which is a solid region, together with a curve in the complex plane, which describes the surface waves. Now, you can't make a classification of the spectrum easily into absolutely continuous spectrum and singular continuous spectrum, etc., because you do not have a proper spectral theory for non-self-adjoint operators. However, it does seem at least plausible that you could analyze the spectrum in a different way, which is to say that this solid region is one type of spectrum, and the curve is another type of spectrum. Now, of course, in this case, there is, for any bounded operator, a notion of essential spectrum and inessential spectrum, but both the curve and the solid region are essential spectrum, so that doesn't get you anywhere. And I could tell you how to distinguish between the curve and the solid region by a further classification of the spectrum, but I've only got an hour, so I'm not going to do so, but it can be done. In the self-adjoint case, it's easy. In the self-adjoint case, the bulk spectrum has got infinite multiplicity. It's purely absolutely continuous and has infinite multiplicity, whereas in the example I just showed you, the multiplicity of the spectrum on the curve, which is the surface waves, is just going to be 2 at every point. So you can distinguish that way. Okay, now I'm going to go on next to a bit closer to the real interest of this group, which is random potentials. So once again, I'm now in n dimensions. We've got a constant, a translation invariant operator, which is going to be some sort of nearest neighbor interaction, but with different constants depending on which direction you're going, together with a potential, which is taking values in some closed bounded set, and I'm going to call it pseudo-random if, when you translate such a function, you can basically reconstruct any other such function. Now, this would be the case if, for example, the potential was chosen randomly and independently at every point of Zn with values in this target space M, and you were given a possibly uniform distribution of probability distribution on M. So the idea is that this actual definition doesn't actually specify a measure, and this is both inevitable and also, it could be argued, is a weakness. But it's inevitable as follows. If you're looking at the infinite volume problem directly, then and let's suppose M has just 2 values. You have some distribution, but it's got to be either plus or minus 1. Then if you want a sequence of 1,000 ones, somewhere on the infinite line it will be there. And if you want a sequence of 1,000 alternate plus or minus ones, then again, somewhere in the set, if you choose them randomly, it will be there. So this potential, in order, when I'm calling it pseudo-random, it includes somewhere along it, translated incredibly far away possibly, a copy of almost anything you can think of. So what you're getting by looking at this spectral theory is actually contains the spectrum of any other particular choice that you might make. And that's just a feature of it. What you could say is that I'm looking at basically the universal estimates which contain the spectrum, or universal spectrum, pseudo-spectrum if you like, something, whatever you like to call it, which contains the spectrum of all the genuinely interesting operators. Okay, so one extreme is that the entries may be random and independent, but of course it could equally well be that you say that the correlation between the values at neighboring sites is very close to 1. So you'd if the set M were finite, you'd have large regions in which you had one constant value with random boundaries, and other large regions in which the potential had other values. And of course these two operators would, in a finite context with periodic boundary conditions, have quite different spectra, but both of these spectra would be contained in the spectrum of the infinite volume operator that I'm talking about. if you have two such pseudo-random potentials, each of them contains large sections of the other if you move off far enough, and so you shouldn't be surprised that both the operators actually have the same spectrum. I mean, this is the kind of result which we're very familiar with in the self-adjoint theory. You can also define a localized spectrum, but I think I will have to go past that, and the localized spectrum is again the same for any two pseudo-random potentials of this type. But now I want to shift emphasis. If you have a periodic potential with values in this set M, then the spectrum of that periodic operator can be computed by the block wave analysis. And that spectrum will be contained in the spectrum of the one which is got a pseudo-ergodic, a pseudo-random potential. So by choosing a variety of different periodic potentials or other things for which you can actually compute the spectrum, you can get things inside the spectrum of the operator we're interested in. So these are inner estimates of the spectrum. I want also to discuss the possibility of getting outer estimates of the spectrum. And this is something that's not quite so easy, particularly if the potential is pseudo-random. One of the ways of getting an outer bound on the spectrum is to use a numerical range defined at the top of this screen, which is always a convex set. And actually, numerically, it's easy to compute. You look at the self-adjoint operator, e to the I theta a plus e to the minus I theta a star. That has a bottom of the spectrum. If you can compute the bottom of the spectrum of self-adjoint matrices relatively easily. And then as theta varies from 0 to 2 pi, you get a curve which actually goes around the boundary of the convex set, which is the numerical range of the operator. So this is a very well-known and easy computational procedure for finding the numerical range, and the spectrum of the operator is always inside the numerical range. However, it's relatively easy. It's also rather crude. And if you want to get more information about the spectrum than you can from the numerical range, then the following idea gets you somewhere. I'm going to start off by taking a polynomial in the operator. And there is a spectral mapping theorem, and this is true for for non-self-adjoint operators, not just self-adjoint operators, which says that if you look at the spectrum of a polynomial in A, the middle thing on the top line, this is actually exactly equal to the polynomial in the spectrum of A. And of course, the spectrum of the polynomial in A is contained in the numerical range of the polynomial in A. So that means that the spectrum of A is contained in this set. The set of Z, such that P of Z lies in the numerical range of P of A. And P of A, I mean, you know what your matrix or operator is. You can calculate what P of A is relatively easily. You can then calculate the numerical range of P of A, and then you have to find all solutions of the polynomial of Z lying in that convex set. And this gives you a new set, which is no longer convex. And you can do this for all polynomials of degree less than or equal to n, and you get a set num sub n of A, and these actually, as you make the degree higher, you're taking a larger intersection, they get smaller, and the interesting thing is that as you go n to infinity, the end result is in fact the spectrum of the operator itself. So if you're willing to calculate numerical ranges of reasonably high degree polynomials in an operator, which is numerically feasible, then you can get better and better approximations to the spectrum of the operator. So, I mean, this is a theorem of, well, it's got a rather complicated history, but Neven-Linner and Greenbaum did it not using these numerical range ideas, but using Hull ideas. This gives you exactly the same result for every n, and therefore also in a limit, but it only works for bounded operators because the norm of P of A only makes sense if P of A is a bounded operator. Whereas the other definition makes sense for unbounded operators because the numerical range of an unbounded operator may well be quite easy to calculate. Okay, so that's a process, and now the question is, can you actually implement it? And here is an implementation for the second degree polynomials. I mean, here is a second degree polynomial, z minus c squared. And as you let c vary, you are basically generating all second degree polynomials. So this process is attempting to compute the second order numerical range rather than just the numerical range itself. And it assumes that the operator can be written in the form c plus is plus v, where c, s, and v are all self-adjoint. Now, the idea that I've got here is that for the kind of operator we're looking at, the potential is the diagonal part of the operator, and that is real valued, so that's self-adjoint. And the other two terms are the a above the diagonal and the b below the diagonal. These are, you can apply the Fourier transform to, and they become multiplication. It becomes multiplication in the case of a right translation by e to the I theta, in the left translation by e to the minus I theta. C and S stand for cos and sine in that representation. So now I'm not quite cos and sine because you have to have, they really, C is a certain multiple of cos and S is a certain multiple of sine. So rather than having S squared plus C squared equals 1, I've got a certain combination is less than or equal to 1. And the claim is that if you have a decomposition of that kind, then you can get a statement that the spectrum, any point in the spectrum satisfies an inequality of this kind. Now, what are all these constants? Lambda and mu appear in this thing, and they come from the two constants a and b, which are the entries above the diagonal and below the diagonal. Gamma sub c is the distance from C to the spectrum of the potential, which, if you know what the potential is, you can see how that depends on C. C is an unknown parameter, so this is true for every value of C. It says that the spectrum lies in a certain set. That is the numerical range with respect to that particular quadratic polynomial, and now you vary it over all possible quadratic polynomials, and you get the second degree numerical range. Well, the proof involves various operator inequalities for the square of the operator, and I'm using this fact that we have to look at the bottom of the spectrum of operators of that general type. This is only one of various strategies you can do for trying to find lower bounds on the self-adjoint part. But as I said, V is this part, and S and V are the sine and the cos operator after taking the Fourier transform, multiplied by suitable constants which depend on A and B. So now I'm going to show you some examples which will illustrate this, and they by no means say everything about the spectrum. So we've got a two-dimensional operator. The constants A1 and A2 are 3, so that means the shift to the right has a constant 3 associated, the shift up has a constant 3 with it. B1 and B2 are -1, so the shift to the left and the shift down have constants -1. -1 is a rather surprising value. You might think you ought to confine your attention to positive coefficients, but you can do exactly similar things with that. You get rather more interesting diagrams if you take the A's to have an opposite sign from the B's. There's no reason why I should take A1 and A2 equal and B1 and B2 equal to each other. The theory works just as well if I don't, but that was a choice. And in the particular diagram I'm going to show you, you are having the potential just taking only two values, plus or minus gamma. They're chosen randomly and independently, and so there is a spectrum, and here is the spectrum. Now this is M is 48, so I It's rather a long time since I did this, but I think that means the matrix, the lattice is a 48 by 48 lattice with periodic boundary conditions in both directions. So the matrix that you're actually looking at is got size 48 by 48 in each direction. And that's why there are rather a large number of eigenvalues here. Okay, so there are various things. Here's the spectrum. This particular case seems to have two eigenvalues here and here, which are apparently a little anomalous. I don't know whether this is computational error or not, but it's fairly clear, I think, that the spectrum all lies within a certain curve. And the first question is, can you actually prove, I don't have the answer to this, but this is a question, can you actually find a way of identifying the curve such that the entire spectrum of this infinite volume operator actually lies within this curve and fills up the whole region inside that curve? What can I say? Well, of course, what I'm doing is looking at an infinite volume operator, and so I'm taking, there's no probability measure needed to specify what this infinite volume operator is. If instead of taking the values at each point, each lattice site independently of each other, I used some correlations, I would probably get an entirely different spectrum. What I can show is that here is the ellipse that you get as the spectrum if you take the same operator but with the potential which is identically equal to plus gamma. So rather than taking it periodic, you take it constant. Here is the spectrum that you would get if the potential was constantly equal to minus gamma. In those two cases, you can work out what the spectrum is by using Fourier transforms. This curve is the curve that you get by using this second order numerical range, and similarly down here. What I can say then as a result of this analysis is that the spectrum must lie underneath this curve, above that curve, to the left of this part of the ellipse and to the right of that part of the ellipse. This particular spectrum was generated by taking random independent entries at every point. If you take a bigger lattice with periodic boundary conditions, you get exactly the same shape, but you get a denser distribution of points inside the region. If you take a different properly randomly generated potential, then you get a different shape, but they all lie inside that region. We don't know how to calculate the density of the eigenvalues at any particular point, and we don't know that these curves that I've said the spectrum lies within gives you the optimal bounds in 2 dimensions. However, Carmen Martinez, who did this work with me, actually did a fairly thorough analysis of the corresponding problem in 1 dimension, and even then it's not elementary, and found that in a variety of cases the bounds that you get by using the second order numerical range actually gives you precisely the right result. That is, you get certain curves and the spectrum must lie within those curves, and you find that you can, when you do the examples numerically, it's not just numerically but actually theoretically as well, the bounds you get from the second order numerical range actually are precise, sharp.
What was assumed about the diagonal elements of this?
This is a 48 by 48 lattice with periodic boundary conditions, and the values at all of these sites are chosen independently and randomly. What distribution? Probably Gaussian. No, it's plus or minus gamma, so it's just equal probabilities for each of the two.
Well, it's symmetric. The picture is symmetric
Yes.
Because it's a real metric.
Yes.
But it also could be symmetric with the y-axis.
Yes, indeed.
It doesn't look, I mean, this airplane area.
Yes, but we're looking at a particular sample.
I understand. But there seem to be more points on the left. There don't have to be exactly. Why not? We're entering already discussion.
You're saying it's too far. Is it? I got to finish within a few minutes? Or? Yes. Yes. You think it looks too far away from being symmetric. So my final example is here. Completely different appearance. Here, the coefficient for going up or to the right is +1. The coefficient for going down or to the left is -1. So it's very antisymmetric. But the potential is chosen in the same sort of way. This is a two-dimensional example. The spectrum looks entirely different. The theorem is that the spectrum lies entirely to the right of this vertical line, to the left of that vertical line, to the right of that vertical line, and within those two curves. That's what you get from second-order spectrum. Now, second-order numerical range. Whether you get a better result by using higher-order numerical ranges or not, I don't know. But as I said, in many one-dimensional cases, the second-order numerical range gives you the sharp information. If this doesn't give you the sharp information, then you can go to higher-order numerical ranges, but then you've got a lot more work because you have to solve cubic equations or quartic equations, and it's not so easy to do that theoretically. Well, whether it's mirrors, you see, if you look at this one, then this has a dislocation here, but it also has a dislocation here, because if it's periodic, you have minus plus going up here and minus plus going up here. So where was this? In the numerical calculations that Hinchcliffe did, he took an odd matrix there. So that means there's only one dislocation. The general symmetry, yes, you would expect a symmetry with respect to complex conjugation and x goes to minus x in this example. Yeah.
Is that related to the eigenfunction of that eigenvalue? Does that eigenfunction have exactly the same symmetry, or is it at all related if you induce more dislocations which are symmetric? You expect more of these disjoint points?
I'd have to be given some notice. I mean, you'd have to do some calculations.
Yeah. What do you mean exactly by pseudo-random? Because usually pseudo-random is something that's a deterministic process that produces something that looks like random, like what we do on the computer. Something different.
I only wanted to draw attention to the fact that the notion I'm doing is entirely topological and doesn't involve any measure. We're looking at all potentials which map Zn to a compact set. Now, this is an infinite product of m to the power of Zn, which is an infinite product of compact sets. So we've got a compact class of potentials. And I'm calling it, well, maybe this is a bad name, but I'm calling it pseudo-random if the translates of the potential are topologically dense in the set of all potentials. But this has got nothing to do with the choice of any probability measure. It's a purely topological notion.
So for the usual hopping process, say the self-adjoint sort of tight binding model, there is this whole machinery of, I guess, green function perturbation theory for disordered problems or so-called T-matrix. For these localized defects, and I was trying to think through during your talk whether,
You mean this kind?
like for example, if I take a localized defect someplace, that one, if this was a standard tight binding sort of hopping problem, one could try and get an approximate sort of sense of what the states look like, what the spectrum looks like due to that defect. And it's not clear to me, is there no usefulness whatsoever for the sort of usual green function type approach?
Well, look, in this particular case, if this is all you're interested in, it's actually fairly simple.
Right.
Because if you look in the vertical direction, then it's periodic with period 2. So you can start off by doing a block wave analysis in the vertical direction. Once you've got that, you've now got a family of one-dimensional problems indexed by an angle theta, and then each of those might have a discrete eigenvalue or a few discrete eigenvalues, and as the parameter in the vertical direction changes, that eigenvalue moves around. So this is a standard sort of problem which occurs, it has actually been studied for many, many years, where you have surface waves. And of course you could put in an extra complication, which is to add in a perturbation of compact support, finite support, in which case that would not change the essential spectrum, but it might add in some extra isolated eigenvalues to this. But you have to be very careful not to believe that what you would like to happen does happen. If you add in a localized perturbation, finite support, finite rank perturbation, it can't change the essential spectrum. People tend to think that this means that all that can happen is that you produce some isolated eigenvalues which weren't previously there. That's wrong. It's quite possible that if the original spectrum has a hole in it, that is, if the complement of the spectrum is not connected, then adding in even a rank 1 perturbation will fill up that hole completely by means of a continuum of eigenvectors. The theorem is, in the self-adjoint case, and in many cases, that if the complement of the spectrum is connected, then adding in a compact perturbation can only produce most countably many isolated eigenvalues, which can only accumulate on the original spectrum. But if the spectrum has a hole in it, which in these examples can easily happen, then you can fill in an entire region of hole in the spectrum by means of a continuum of multiplicity 1 eigenvalues. So one shouldn't be too ready to assume that what happens in the self-adjoint case also happens in the non-self-adjoint case.
Brian, so you are saying that Wein's theorem is not correct. You can change the essential
No,
spectrum. No?
you're not changing the essential spectrum.
But
The thing
if
which
you
you-
are adding a continuous, this is essential spectrum.
No. The prejudice that non-essential spectrum coincides with isolated eigenvalues of finite multiplicity is not only a prejudice, but a true statement in the self-adjoint theory. It's not a true statement in the non-self-adjoint theory.
So what is the definition of the essential spectrum then?
Well, there are, of course, at least 5 definitions of essential spectrum in the non-self-adjoint theory. The spectrum I'm referring to in this context is you look at the quotient of the bounded operators by the compact operators. It's called the Kalkin algebra. You look at the operator you're interested in, map it to the Kalkin algebra, and calculate its spectrum there. Another way of putting it is that you say 0 is not in the essential spectrum if there is something which acts as an inverse up to a compact errors. But there are several different definitions of essential spectrum, and none of them will get around the problem, which is that you can change the spectrum of a you can change the spectrum of a unitary operator hugely by adding on a rank 1 perturbation. And that's because a unitary operator can have the spectrum is the entire circle with a hole in it. the theorem is that if you look at the unbounded component of the resolvent set and you make a compact perturbation, then you can only produce a discrete set of eigenvalues in the unbounded component. But in any bounded component of the resolvent set, you can change it entirely. This is related to the index theorem, by the way.
In the physics literature for random Hamiltonians of different kinds, there's well-developed theory for what happens to the density of states in regions where it's very small, which goes under the name of Lifshitz tail state. Is there something similar for non-self-adjoint operators?
Well, I think this is a point where we'd have to discuss it in order to be sure that I knew what you were asking. One thing I did mention, but I had to go past it, was the idea of localized states. Now I'm not going to find it. It is entirely possible that with an infinite volume operator of this type, you could have a sequence of unit vectors which got closer and closer to being eigenvectors. That is, the vectors themselves, or functions themselves, march off to infinity. The eigenvalue equation is satisfied more and more accurately as they march off to infinity. And the variance of the vector, that is the spread around its mean value, actually stays bounded. This again can't happen in the self-adjoint theory. But it's quite easy for it to happen in the non-self-adjoint theory.
Localization in some specific sense.
It's localization, but not for eigenvectors, for things which are getting closer and closer to being eigenvectors. But the mean values are going to infinity, the variances are staying uniformly bounded. So that phenomenon can happen.
Please.
Yeah. I just would like to develop a bit the previous question. In the self-adjoint case, there are two definitions of the density of states. One starting from finite volume and just counting eigenvalues and then dividing by volume, getting the limit. And second, just for infinite operator, you just take the diagonal, the kernel of the resolution of identity, expectation of the diagonal entry. And these two definitions coincide, of course, in self-adjoint theory. Since you claimed several times that there is difference between infinite and expanding operators, natural question whether these two definitions coincide in the simplest case of three diagonal matrices. In your case,
Well,
maybe that new
Yes.
spectrum that you mentioned several times, it's it's density there of eigenvalues or their number is growing less than the volume in first power, and then it will not contribute to the infinite volume density.
I mean, I'd be rather doubtful about this because of what I said up here. You can have a point which is well away from the spectrum, for which the resolvent norm goes to
Yeah,
infinity.
but what is
And
the
should that
multiplicity of this point when a volume tends to infinity?
not just that point, but whole region. Every point in that region would have an approximate eigenvector. Every point in that region would have a resolvent norm going to infinity as the size of the thing gets bigger and bigger. So in
This I
the
understand, but nevertheless.
But probably we should finish our discussion and then, you can discuss it privately. Let us thank you.